Hey guys, in this video we're going to be focusing on lesson 3 of our first unit, which is all about independent variables, dependent variables, domain, and range. So let's go over tables first. It says the United States Mint is responsible for producing and distributing circulating coins that are used by people every day to buy and sell goods. The table to the right shows how many coins were produced each year from 2001 to 2011. First question, does the table represent a function? Justify your answer. Well, remember that a table represents a function if each input has exactly one output. And if you look, there is not a single year on here that repeats and having a different output. So the answer is yes, each input has one output. Okay, 2, what is the independent variable in this situation? Remember, independent means input. So in that case, that's our year. 3, what is the dependent variable? Okay, dependent is always your output, so that is the circulating coins produced. All right, number 4 is the domain. So remember, when you have a table, your domain is written as a set, and you're going to list every input in order from least to greatest, and you don't have to write any of the repeats. But again, we don't have any repeats because this is a function, so I'm just going to list each year in order, starting with 2001, all the way to 2011. All right, and then similarly, when we find the range, we're doing the exact same thing, except this time we're focusing on the outputs, our y values, which is on the right side of the table. So remember, it needs to be in order from least to greatest. And this time the table is not ordered, so we need to find the smallest, which in this case is 3.5. And then we're gonna go all the way up until the biggest one. 6.4, 8.2, then, nope, 10.1, and then 12. Let's see, 13.2. We have two 14.4s, so we only have to list it once. Then we have 15.3, 15.5, and 19.4. That should be all of them. And that's it for this problem. Let's try the next one. Let's review the same thing, but with a graph. Now remember, a graph that has points that are not connected is called a discrete graph. All right, so we're gonna do the exact same thing we just did. Same 5 questions. Does this graph represent a function? Justify your answer. So remember, if each input has exactly one output, or if it passes the vertical line test, the graph represents a function. So if I look here, 1 has only one output, 2 has only one output, 3, 5, 6. Each has only one output, so that means this is a function. Yes, each input has only one output. All right, and then remember, the independent variable is always your input, which is always your x. This is your x-axis, so the number of free throws made is the independent variable. Okay. Dependent then means the total points scored. Okay. Domain Since this is a discrete graph, it's done a lot like a table. So we're going to list each of the inputs for the domain using a set. So we have 1, 2, 3. Then we have 5 and 6. Those are all the inputs. And then for the range, we're going to do all of the outputs. Okay, so lowest one is, let's see what we're counting by here. 2, 4, 6, 8, so 2s. So this is 6, 8. Always check the scale. And then we have 2 of them at 12, so I'm only going to write that once. And then we have a 14. And that's our range. All right, moving on. If I can get the paper to turn. There we go. All right, many cell phone plans have an option to include more than one phone. The function for the monthly cost of cell phone service from a wireless company is f of x equals 25x plus 200, where x is the number of phones of the plan and f of x is the total cost. All right, so let's talk about number 1. It says, what does the 25x in the function represent? And what about the 200? Well, 25x, I know that x is the number of phones, which means 25 must be how much each phone costs. So 25x means each phone line costs $25. Now the 200 on the end is a constant. There's no variable with it. So that must mean that that is some sort of flat rate that the company has. So I'm just going to add that on here. The 200 is a flat fee or flat rate that the wireless company charges. All right, that's number 1. Number 2, the independent variable. Remember, independent is always your input, which is always your x. So x is the number of phones. Number 3, the dependent variable is the y, or f of x in this case, which is total cost. Okay. All right, it says, what is a reasonable domain for this situation? Okay, so number 4, we need to think about what is the least amount of money that someone could pay and what is the most amount of money that someone could pay for this wireless company. So if you think about it, how many phone lines, or what is the least number of phone lines that you could have for this company? And that would be 0, which would be silly, but it is possible to have no phone lines. So I'm going to say that this reasonable domain starts at 0. And what is the most number of phone lines you can have? Well, there really is no limit. So that can go on forever, which is infinity. So that means this domain is from 0 to infinity. Now let's think about the range. Remember, range is talking about total cost. So the least amount that you could pay versus the most amount that you could pay. Well, let's think about that for a second. If I have no phone lines, that means x is 0. 25 times 0 is 0, but no matter what, I'd have to pay this $200. So that means I'm starting at $200 no matter what. That's a fee that has to be paid. Now, I can have an infinite number of phones, which means the total cost could also be infinite. So that means it goes up forever. So I could pay anywhere from $200 to infinite number of dollars, depending on how many phones I have. All right, number 6, does this equation represent a function and how do you know? So you need to think about, is there a number of phones that I could have that could produce more than one total cost? So for example, if I only have one phone line, is it possible for me to have 2 different total costs? And the answer is no. If I have one phone line, it's 25 times 1 plus 200, which is 225. There is no possible way for me to pay anything but 225 in this case. So this is a function. Each input has only one output. All right, and the last question is one that we haven't done before. It says, what would the graph of this situation look like? So number 7, what I'm going to do is I'm going to sketch a graph for what is going on here. Now, this is a real world scenario. I really only need the first quadrant because it's impossible to have negative phones, and it's also impossible to have negative total cost. So I know that my input is number of phones, and I also know that my output, or my Y, is total cost. So I'm going to rely on my domain and my range to help me draw this graph. I know that my X is going to start at 0 and my Y is going to start at 200. So I'm just going to make an arbitrary point, and I know that this would have to be 200. That's my starting point right there. Now I know that each phone that I add to this line, or this service, is going to add $25 to my account, my total cost. Now, since that is going up by the same amount each and every time, this graph ends up being what we call linear, or a line. So I know it's going to increase as I go up, just like this, and I'm going to put an arrow on the end because it can go up forever. And that's it. That's a rough sketch of what this graph looks like. All right. Now let's talk about some real-world scenarios that don't give us any kind of graph or table or equation to look like, and we'll talk about all of those same things. All right, it says, as Nora goes through her day, the number of text messages that she has sent increases. Okay, so let's start with number 1. What is the independent variable in this situation? When I'm trying to decide a question like this, I always figure out what my 2 variables are first. So I know that Nora's going throughout her day, and we're talking about the number of text messages that she has sent. So that means we're dealing with time as it's going on throughout the day, and number of text messages sent. Well, the number of text messages that she has sent depends on how long the day has been going. Obviously, that's increasing throughout her day. So I'm going to say that time is my independent variable in this case, and that number of text messages sent is my dependent. All right, now we got to talk about a reasonable domain and a reasonable range. So this is very similar to the last problem. So remember, my domain is all about time. So the starting point of time is literally 0, right? When you wake up in the morning, that's the beginning of the day. Okay, now time also is infinite. It goes on forever. So I know that that is going to be part of my domain. And then similarly for my range, the least number of text messages that Nora can send is 0, and the most is infinite. She could send a lot of different numbers of text messages throughout the day. That could be anywhere from 50 to 1,000. Who knows how many times she texts during the day. All right, and then number 5, what might the graph of this scenario look like? All right, so there's a couple ways that we can think about this. We weren't given much context to go off of, so this is probably going to be another linear graph, but also it's going to depend on what Nora's doing throughout her day. Maybe sometimes she stops texting. So it's kind of up to interpretation in this case. But we know one thing is for sure. Our input is time, and our output is number of texts. We also know that time starts at 0, and so does number of texts. So this is my starting point, okay? So as she goes throughout her day, it just increases like this. Now, if we were given more of a story, we might be able to make the graph look a little bit different based on that story, but we weren't given one, so this is what we're going to go with. It is a linear graph because they didn't tell us if she sends more at different times or things like that. So we're just going to assume that as time goes on, the number of texts she sends increases. All right. The air pressure inside of a soccer ball decreases over time. All right, same idea here. Number 1, what is the independent variable? Well, first of all, our 2 variables, once again, time is one of them, and we also have air pressure. Now, the air pressure in the ball is going to depend on how much time has passed, so that means time is my input, my independent variable, which means air pressure is dependent. All right, a reasonable domain for this scenario. Okay. Now, this one's a little bit complicated because you cannot have infinite air pressure in a soccer ball, but we also don't know what is the greatest amount of air pressure that you can have inside of a soccer ball. So we are going to say that once again, it goes to infinity because we don't know what the greatest amount that it can have is. So infinity doesn't necessarily work here, but because we don't have anything else to go off of, we're just going to leave it at that. What we do know is that 0 air pressure is the lowest it can be. And as I'm speaking, I'm realizing that that is actually the range because air pressure is our output. However, our input is time, and time still starts at 0 and goes on forever. So our domain and our range are the same here. All right, and then number 5 is all about the graph. So we're going to make our graph. I know that time is my input and air pressure is my output. Okay, now the difference with this one is we know that the air pressure is decreasing. So I should not have a graph that is increasing, I should have one that is decreasing. So I'm going to make an arbitrary point. Let's say it starts here, and at some point it reaches 0 here. And my graph is just going to go straight down between those 2 points. Once again, I can't have negative time or negative air pressure, so I don't want to go past the x or the y axis because that would not make sense in this case. So that would be the graph that represents this scenario. All right, we got a couple left. A kicker on a football team punts a football downfield. All right, so first problem here. What is the independent variable in this scenario? All right, so independent. Okay, so we know that this football is being kicked. They aren't giving us much else to go off of, so you have to think in your head what this looks like. So what is happening to the football here? Well, as time goes on, the football is increasing in height. At some point, it probably reaches a peak and then comes back down again. So we're talking about time and maybe height of the football or distance of the football. It could be either one, but regardless, time is going to be our independent variable here. And then number 2, we could either talk about height of the football or distance the football has traveled. I'm going to choose height just for fun. It's totally up to you in that case. All right, number 3, what's a reasonable domain for this scenario? All right, so domain is time. So we know that it's from 0 to something. We don't know how long this is going to last. So it's kind of arbitrary here. And it kind of could have been arbitrary for the last problem as well. So we know that time can go on forever. But in this case, at some point, that football is going to hit the ground and our time is over. So let's make up an arbitrary time here. So let's say it goes from 0 to, I don't know, 10 seconds. And then our height starts when the football is kicked. It's being punted, which means it's going to start off the ground a little bit. So let's say it is kicked 2 feet off the ground, and the highest it gets is 50 feet. These punters are really good, or maybe not so good. All right, and then number 5 wants to know what the graph looks like. Well, if you chose time and height, this is what your graph would look like. If you chose time and distance, it would probably look a little bit different. So I know that time is my input and height is my output. I know that my graph starts, or the height of the football rather, starts at 2 feet. At some point, it reaches a height and comes back down, right? That's what happens with gravity. But I also said that it's only going for 10 seconds. So I'm going to say that is my reasonable domain, and therefore that's where the graph ends. So it's starting here. The punter kicks the ball, it goes up, 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 and at some point starts coming down, 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 and ends right there. And we're going to say that this height right here is 50 feet because we said that's the highest that the football goes. All right, so that's a reasonable domain and range, and that's what the graph would look like. If you chose time and distance, it would probably be linear because as time goes on, the distance the football has traveled increases, and it would stop at some point. It wouldn't keep going forever. All right, real world scenario number 3. The number of items a store sells decreases as the price of the item increases. All right, number 1, what is the independent variable? All right, so what are we talking about here? Number of items sold and price of the item, okay? So the number of the items that are sold is depending upon the price of the item here. So that means my independent variable is price of item. Okay, and then 2 is going to be my dependent variable, which is number of items sold. Okay. Number 3, a reasonable domain. All right, so once again, we're gonna have to think a little bit. So price of the item. The cheapest the item could be is 0, right? Now, a store probably wouldn't be giving things away for free, but it is an option, okay? Now, there is an infinite number of prices that a store could have something cost, but obviously the higher something is, or the more expensive something is, the less of something they will probably sell, which is what this problem is saying. It's decreasing here. So we can either make up an arbitrary point, or we can say that the price can go on for infinity. Because I don't know what kind of item we are selling here, and I don't have a price to go off of, I'm just going to say infinity. When you have problems to do on your own later, I will definitely give you better problems to work with. Now 4 is the range. Now the least number of items that a store can sell is 0. The highest is obviously however many they have in their inventory, but we don't know what that number is, so I'm once again just going to call that infinity. And then the last question here says, what does the graph of this scenario look like? So here's my first quadrant. I know that the price of the item is here, and the number of items sold goes here. Okay. Okay, so we did a problem like this recently where I gave you the graph. I know that both the domain and the range can be at 0 at some point, and that they can go on infinitely. So obviously, if a item is free, you're going to get rid of a lot of them. So I'm going to say that my graph starts up here somewhere. But as the price increases, the number of items sold decreases until at some point you're selling no items. So this is what the graph should look like. And that's it. That's independent variables, dependent variables, domain, and range.